Our next presentation is by faculty member Professor Majdi Abou Najem from the Department of Civil and Environmental Engineering. I should stay away from this. And his talk is entitled Humanitarian Engineering Opportunities for Poverty Alleviation.
Okay, good afternoon, everyone. So a quick background. Last Wednesday, Matthias gave me a call to my office, and he was talking me through having a talk in this conference. As he was talking, I was trying to think and recite some, kind words of apology as he was talking. But when he mentioned the title, I couldn't but accept, because this is a title that is very close to my heart. So today I'm going to talk about humanitarian engineering and target some opportunities for poverty alleviation. So as a start, what a better start than going through a quick definition. This is a definition from the Humanitarian Engineering program at Oregon State University, one of the leading universities in humanitarian engineering, which defines humanitarian engineering as the use of science and technology-based solutions to address basic human needs and improve quality of life, particularly for those in underserved communities. So when you see words like basic human needs or underserved communities, one tend to undermine the engineering value of it. I've noticed this with some of our engineering students where, I'm not going to work with this, I need to work on top high-tech projects, I want to see or work on the tallest building or the biggest span bridge or whatever. And it's always thought of those issues as secondary. So once talking about those topics starts having questions like these: how much or perhaps how little engineering is there? Am I burning my career if I start that low? Is there any sophistication or complexity to humanitarian engineering? And any chances I can satisfy my nerdy engineering ego while working with low tech and low cost or low budget? So in my talk today, I hope I'll be able to convince you with the following three things. I would be trying to clear some of the misconceptions about humanitarian engineering. I would be introducing some of the case studies of humanitarian engineering that I'm either aware of or worked personally on, and challenge you to think or consider a different path. So starting with the first one, some of the misconceptions. When we say engineering, and I can't think of a nicer presentation to follow Professor Shdid's talk. When we talk an engineer, this is the image that we have. Somebody with, a nice tie, nice clothing, working on in a very clean lab or on a very sophisticated project. These are the projects that some classic or boxed perceptions of engineering. I'm excluding construction engineers, so I did not have a dusty figure for that, but this is the image that someone would have in mind. So when you compare this with images like these, one would tend to say, are those really equal? And I'll try today to convince you that yes, they are. They are indeed different, but they are equally sophisticated, equally challenging, if not even more. So I'd invite you to think twice. First, think impact. How many lives can you impact by working with poor people? How many game changer can you become if you target the humanity's basic needs? I would like to share this photo. This is an image that I took from a Syrian refugee camp. I want you to think complex. How many engineering problems can you see just from looking at this image? Any idea? Okay, this is just to name a few, right? So this is some set of those, some solid waste management, water quality, water supply, heating and cooling, thermal insulation, energy supply, and the list continues. And if you want to satisfy your nerdy side of engineering, each one of those is governed by a wide range of physical laws. So as you go into a camp, you don't forget about the equations, about the fundamentals that you learned. There's a lot that you can do, and you don't need only to use those complex equations or tools that we teach you here to apply only on complex and sophisticated projects. So I hope this clarifies some of the misconceptions about what humanitarian engineering is. After all, engineers are always problem solvers. We all share the fact that we want to make the world a better place. I fully agree with Dr. Shdeed's remarks. No one can do this better. And yes, we are the best. This is a fact. So let me introduce some of the case studies. For the interest of time, I'm going to talk only about one case study, which is the case of the WASH sector in Lebanon. WASH is an acronym that stands for Water, Sanitation, and Hygiene. And this became a big problem, particularly on the onset of the Syrian crisis, so from 2011 and into today. Let me give you some background. So this is Lebanon pre the Syrian refugee crisis. A 2010 report showed that every person in Lebanon have access to only 926 cubic meters per capita per year. To me as a hydrologist, this is a very scary number. The moment the number goes below 1,500 to 1,200, we are below the scarcity line. And that was in 2010, and that was before Syrian refugee crisis started. And if you look at the tables, if you look at the red boxes, you can see the mismatch between the supply and the demand. The story doesn't look any better with wastewater. So only 60% wastewater network coverage in 2010. And guess what? There are some 60% network coverage, but only 8% of our wastewater is treated. The rest is transported just from one place to another and dumped without any treatment. Into the Syrian crisis, the Syrian refugee crisis, 41% of the refugees only have access to flush toilet facilities as compared to 83% of the Lebanese, meaning that the remaining are just generating waste without even the very least human needs. So these are some of the technical questions that arise. How can Lebanon's fragile ecosystem absorb the environmental load from WASH? We are already stressed even before the crisis. How to deal with some extra 34 to 56 million cubic meters per year of wastewater, 40,000 tons of BOD, which is one of the parameters that we measure for wastewater. Are things getting any better? Well, 23% have no access to bathrooms in 2016 as compared to 10% in 2010. So we're not moving into the right direction. And can current interventions cope with a dramatic development? Are they enough? This is just an image that I took from my first visit to a Syrian refugee camp. And you can see, too bad because of the lighting, I'm not sure if you can see well, but a typical bathroom is nothing but some convenient, some privacy space, a separator, and there is a hole in the ground with nothing after that. Whatever happens in the bathroom will just basically stay there, it settles down, and if the water table is high, everything will get to the water table and to the groundwater that we use. This is indeed an example of that. So this is actually the first water cycle that I show my students in the engineering hydrology class. Who can guess what this arrow is looking for? That's a well, right? You can see the pump. Do you know how deep the water there is in that area? This is in Barrelies. This is less than 10 meters. That specific well was 9 meters only. And you can see this line in here. This is a wastewater trench. So wastewater is actually seeping into the groundwater, which people are pumping and using within the same camp. This is one of the shortest water cycles I've ever seen. So it lends itself as a perfect case study for a course, but definitely a very sad reality. So We started into interventions some long time ago when we started with the classic systems, working with the Center of Civic Engagement at AUB. We started designing some typical bathroom structures. We adopted some modular systems where everything can be assembled very quickly and also disassembled very quickly, because we were thinking about the exit strategy, and that hopefully those structures can be among the very first few structures that the Syrian population would take back with them as they reconstruct Syria. Now, we took those designs into actual implementation, but as we were designing and doing those, I started thinking that, what are we doing? We're just spending money to basically transport waste from one place to another. None of those areas have an actual wastewater treatment plant. So aren't we just taking wastewater from the immediate vicinity of the camp into just somewhere else, dumping it either into a river, a lake, or into the sea? And this made me start thinking that we need to understand the ecosystem and the ecology around us. And we need to look for alternatives where the treatment happens in place. So we started looking at the system. It's all its inputs, all its outputs. I decided to scratch the word wastewater, because if I think of it as a wastewater, that's a bad thing. And we cannot deal with it unless we have a few $100 million of investments. So why don't we think of it as nutrients? And instead of closing the cycle between the nutrients and the ecosystem by dumping this pollution load into the ecosystem, why don't we close the cycle with the agricultural sector, making thus a hygienically more safe system? So we started thinking about dry sanitation as an intervention. We designed a system, also modular system, the same concept, but we separate the yellow part from the brown part, and we basically treat each one locally at the source. So the liquid part, the urine, is basically channeled into a constructed wetland, and it's basically transformed into biomass. We transformed urine into bamboo and sunflower. The dry part would fall by gravity into a bucket. You leave it for 3 months, and it turned basically into a compost or a fertilizer. This is the system after implementation, and this is also the drawing. This is after implementation. I'm going to go, for the interest of time, very quickly over some photos. Okay. And so you see, this was actually at some point in time the only green space in the entire refugee camp. And it's, if you look at this, you might see sunflowers, I see urine. I'll see if time allows, I'll go back to this project. This is the TAMO project. I can talk to you about how my colleague and friend from Oregon State University, John Selker, is on a mission to build 20,000 weather stations in Africa. You might wonder why does he want to do that. If time allows, we'll talk about this. This is one of the most sophisticated humanitarian engineering problems or projects in the world at this moment. So challenge you to think or consider a different path. This is the last part of my talk that I want you to talk about. Here I want to talk about opportunities. If you are interested in this field, there are so many opportunities that you can consider. Different NGOs at multiple scales, international, regional, or even local. There are international donors and organizations, UNHCR, UNDP, among others. At AUB, we have 2 great centers, the Center of Civic Engagement and the Nature Conservation Center. EWB, Engineers Without Borders. I know that there is a chapter here at AUB, and this is an international initiative. Also development-focused SMEs. There is a lot of investment of money into SMEs these days, and development is actually at the core of the bulk of the newly developed SMEs. In terms of graduate opportunities, I thought of sharing with you some of the best and well-known programs in the US. Oregon State University is my favorite. I am biased. I worked there. Ohio State University, Humanitarian Engineering Center. MIT's D-Lab, and also UC Davis D-Lab. D-Lab is a new concept that emerged. It's the design lab, basically, and it targets development. Colorado School of Mines, and Dartmouth. A few take-home messages before closing my talk. So humanitarian engineering allows for a paradigm shift in aid and development industry. And it's also philosophy to target the full life cycle assessment of a certain problem. It is time that LCA of development projects be considered, and it's time that we look for some holistic and transformative concepts of development. More on the nerdy side of engineering, obviously environmental systems are way nonlinear. Okay, so saving the last 1,000, 10,000, or 100,000 flushes per day is not only as good as saving the first. It might be, due to the nonlinearity, way better. With that, I end my talk, and thank you very much.